The age-old question. How much does Peter Griffin weigh? I mean, how fat is he really? Well, as elusive as the answer may seem, we can actually figure it out using some basic physics. For example, take this clip from the show.
You know what it is?
Sure, it's an apple.
Good, good, good. All right, watch this.
What the heck? What is this? What is this, some kind of gag?
No, that's orbit.
Huh?
You have your own gravitational pull.
Oh, that's a bunch of crap.
Now back to the Three Stooges.
Oh. Oh.
While it's quite an amusing scene, we can actually learn a great deal about Peter Griffin by observing the orbits of the objects around him. Let's take the apple, for instance. We're going to pick some easy numbers to work with here. Let's say the orbital radius is about 0.5 meters. The time that the apple takes to orbit Peter is about 3 seconds. This is a decent estimate, and it's as good as we're going to get. Now, given these two pieces of information, we can calculate how far the apple travels in one orbit. This turns out to be about pi meters. We can also calculate how fast the apple travels about its orbit. And since it travels pi meters in 3 seconds, we can say that its velocity is pi over 3 meters per second. The velocity is going to become important later on, and we'll find out why in just a second. Now on to some physics. We know that the gravitational pull or force between two objects is equal to the constant g times the mass of the first object times the mass of the second object divided by the distance between the two objects squared. We also know that the force required to keep an object in circular motion equals the mass of the object in motion times the velocity squared divided by the radius of the orbit. The force required to keep an object in orbit has to come from somewhere. In this case, we know that it is the gravitational force that is causing the orbit. Therefore, we can set our first equation, g m1 m2 over r squared, and we can set that equal to our second equation, mv squared over r. Then we just need to solve for m1, or Peter's mass. Notice we don't have to worry about the mass of the apple because the mass of the apple cancels out. Eventually, we should end up with Peter's mass equals v squared r over g. Now it's just a matter of plugging in numbers. We know that the velocity is pi over 3 meters per second. We know that the orbital radius is 0.5 meters. And we know that the constant g is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. We should end up with about 8.2 times 10 to the 9th kilograms, or 8 billion kilograms. This translates into about 80 billion newtons, or 20 billion pounds. To put this number into perspective, this is about the combined weight of the population of Great Britain. So yes, Peter, you are very, very fat.